Hello, this talk is about our paper titled Entropy Decay in the Swendsen-Wang Dynamics on CD, and it's part of STOC 2021. I'm Antonio Blanca, and this is joint work with Pietro Caputo, Daniel Parisi, Alistair Sinclair, and Eric Bigot. So first, let us define the model, the probabilistic model we'll be working with. It's the POTS model. It's one of the most famous and useful discrete probability models. And it's defined on a graph, G, and there is a set of spins, 1 through Q. And the set of configurations of the models are the set of spin assignments to the vertices. So every vertex will receive one spin, and the spin will be, we can think of a spin as a number, an integer number from 1 through Q. And Q is the parameter of the model. Then we define a probability distribution, or the set of all configuration. This is known as the Gibbs distribution or the POTS distribution. And it's given by this expression here, where every configuration sigma has a weight e to the beta times m of sigma. Here, m of sigma is the number of monochromatic edges in the configuration. What we mean by that is that the endpoints of the edges will have to have the same spin. So we count the number of edges in sigma that both endpoints have the same, are assigned the same spin in sigma. So beta is a model parameter. It captures the strength of the interactions between the endpoints of an edge. And in applications in statistical physics from this model, beta is associated to the inverse temperature of the systems. And then there is this normalizing constant here known as the partition function, which is just the sum of the weights of all the configurations. Okay? So here is an example. In this case, we have a graph that is a 4x4 grid, and Q equals 2. And we see that this particular configuration here receives probability E to the 12 beta over C. And it is 12 because there are 12 monochromatic edges here, right? So we have 5 red edges and 7 blue edges, okay? So here is another example. If we flip the corner here, we gain an extra 2 monochromatic edges. So the new weight is e to the 14 beta, and then we normalize, okay? So a special case of the POTS model is the case when we only have 2 spins, like it was the case in these examples here. This is not as the easy model, and it's again a very famous and well-studied model in probability and computer science and machine learning and so on, and it goes back to the 1920s. Okay, so an important distinction here between the models is when the model is attractive or repulsive. When beta, the strength of the interaction parameter, is positive, we say that the model is ferromagnetic or attractive in the sense that the endpoints of the edges will prefer to align to the same spins, and otherwise we say that it is antiferromagnetic, where every edge is negative. Okay, so in this talk we're going to be focusing on a particular graph or class of graph, and these are the n vertex cubes of CD. We will see that our results actually generalize to a larger family of graph, but this is the problem that we set out to study was initially on this setting. Okay? So here in our example, this is a cube, in a 2-dimensional cube essentially, and this is a 2-dimensional cube of CD. Okay, so in this setting, right, let's say in C2, in general in CD, we expect, or we know that there is this phenomenon called a phase transition. So there is a critical threshold here for the parameter beta, so that for every Q greater than 2, if the parameter beta is below that threshold, then we have no dominant spin class in a sample from this configuration with high probability. Okay, so what that means is that if we do a sample, if beta is less than beta critical, and we do a sample from the distribution, with high probability will look something like this on the left, where you can see that there is no dominant color. Here, in this case, in this example here, Q equals 3, red, blue, and green. And we can see that we have roughly the same number of vertices of each color class. And moreover, there is no really long-range correlations. If there are any correlation, they will happen locally, right? So this would really look like a very disorganized system with no long-range order. But if we take beta to be larger than beta critical, then there is one dominant color class or a spin class. So for example, a sample will look something like this when there is one dominant color, in this case is the blue one, and then here we have long-range correlations. So vertices that are far apart from each other will exert influence on each other. Okay? And this, for the case of, for the two-dimensional case, the sequence of important works going back to the 1930s and 40s and combined by the work of Befara, Dominic Kupin, in 2010, we now have this picture for C2. For higher dimensions, we don't have quite the picture as complete, but we expected that something like this will happen there. Okay, so our goal here is going to be to sample from you. So this is the computational problem that we're interested in. We like to generate samples, and for this we'll use microchains. This is the approach that we're studying here. And the most most simple microchains is the global dynamics, right? This is a microchain that will pick a random vertex. In each step will pick a random vertex, and then it will update the spin at that vertex or the color at that vertex according to some local rule. By some local rule, it means that it will look at the spin configurations of its neighbors, for example, and will make a choice on the probability of being one color or another. Okay, and there are different ways in which we could define these local rules. So, but in general, all of them are within the same class of global dynamics. Okay? So the global dynamics actually we understand quite well now. There is a long line of work, and essentially we know that when beta is below the critical point, let's say in 2 dimensions, when beta is below the critical point, the speed of convergence, the global dynamics is quite fast in the sense that it converges to the target distribution quite rapidly. But when beta is above the critical point, then we know that it's actually quite slow. It takes exponentially many steps to converge. Okay, I'm being slightly informal here, but what I mean by convergence, but I'll be more formal in a minute in the next few slides. But the important thing here is that when beta is large, this corresponds to the so-called low temperature regime, then the global dynamics becomes slow. And because of that is what motivated the introduction of this other microchain, which is much more sophisticated, much more complex, known as the Swendsen-Wang dynamics. Okay, so here is one step of the chain. Suppose that you have some configuration, right? Some assignment of spin to the vertices. So in one step of this chain, what we'll do is we'll consider all the monochromatic edges in the configuration, and then we're going to remove some of the edges from this configuration, and we do that with some probability, right? So every monochromatic edge is removed with probability e to the minus beta. Beta is the mode parameter. So now from this new configuration, now what we do is we forget the spins and we keep the edges. So now this is how our configuration looks like, our intermediate configuration. And now for each connected component on this on this intermediate configuration that is on the edges, we assign a new spin at random, right? We pick a spin uniformly at random from 1 through q, and we assign it, and it will look something like this, right? Then we drop the edges, and we'll obtain a new configuration, right? So as you can see, this is a quite sophisticated microchain. The steps are quite complex, quite global. Every spin can change can potentially change in one step, okay? But the important thing is that it has the ability of flipping large clusters, right? It can flip let's say from a mostly blue configuration, it can very easily flip to a mostly red configuration because it's choosing the colors at random for each connected component. And this is essentially what makes this microchain quite attractive, because the global dynamics, the reason the global dynamics was slow is because it has a hard time changing from a mostly red to a mostly blue. This is what creates some bottleneck for the microchain, but for the Swendsen-Wang dynamics, that does not happen. Okay, so here is some additional insights about the Swendsen-Wang dynamics. It was introduced, as I just mentioned, to overcome the slow convergence of the global dynamics. It was noticed immediately that it was quite fast in several cases, and it became quite popular. People started using this microchain to sample. But in the mid-90s, we got the first of various results saying that this microchain was actually slow. For some cases, in this particular case, was a complete graph. And for some specific value of the parameter beta, Gordon and Jerome showed that the chain was actually exponentially slow. Okay, and since then we have other slow mixing results. So this is not quite such an isolated phenomenon. So the question that we're exploring in this work is how the Swendsen-Wang behaves on the n vertex cubes of CD, on the cubes of CD. Okay, and now probably is a good time to define what we mean by speed of convergence, and we're going to be measuring the speed of convergence by mixing time, which is the most standard notion of a speed of convergence, and it's just the number of steps that the chain has to take until its distribution is close in total variation distance to the target distribution, in this case, the Potts distribution. And the key aspect of the mixing time is that it assumes a worst possible starting case, right? So we want to measure the speed of convergence in terms of total variation distance, assuming a worst possible starting configuration. Okay. So before I state our results, I need to introduce two notions, right? One of them is the idea of a boundary condition. So here in C2, we are considering for instance, here we have a 4x4 box or cube in C2. And a boundary condition is going to be a fixed configuration in the outside of the box. So we look at the outer boundary and we fix a boundary condition there. I mean, we fix a spin configuration there. And then we consider the Potts configuration in the inside of the box with the conditional on this particular configuration fixed in the boundary, right? So one way of thinking of this is looking at the Potts measure in V union its boundary, right? In the cube union its boundary. And then we fix the spin configuration on the boundary. Okay? So we consider this conditional notion. And another important notion that is quite related to the idea of the phase transition is the strong spatial mixing condition. Right? So this is a decay correlation property, and it's defined as follows. Suppose that we consider a cube, okay? And for the cube, we put two different boundary conditions. We consider two different boundary conditions for the cube, but they're only going to differ on one vertex, right? So here they differ only in the vertex, in the spin of the vertex U, right? So under these two boundary conditions, then we consider any subset in the inside of the cube and the difference in total variation distance between the distributions that these two boundary conditions induce on the red region, on the green region, right? So when this total variation distance decays exponentially with the distance from the region to the disagreement, right? That's when we say that a strong spatial mixing holds. I mean, in particular, we say that a strong spatial mixing holds. We need to quantify this. We say for every cube, for every pair of boundary conditions that differ only in one vertex, and for every subregion of the cube, right? If we get this exponential decay for all of those settings, then we say that SSM holds. Notice the difference with the also standard so-called weak spatial mixing, where we don't consider distance to the disagreement, we consider distance to the boundary. Okay, so this is the stronger notion of decay. Okay, so what we prove is that this strong spatial mixing condition implies optimal log-n mixing of the Swendsen-Wang dynamics on an n-vertex cube of CD. Okay? So that's our main results in this work. Here are a few quick remarks. These results, the bound for the mixing time holds for all Qs and all boundary conditions. The free one is one of them when you have no condition. In that case, our result also holds. The best bound known on this setting was O of n, and this was previous work due to some of us in this paper. And this result is actually quite appealing because it's very similar to an analogous result for the global dynamics that said that SSM implies optimal n log n mixing for the global dynamics. So this could be seen as the analogous result, although the proof techniques are very different. Okay. So as a byproduct of our result, for example, in 2 dimensions, we know that SSM, the strong spatial mixing property, holds all the way to the critical point. So we get optimal mixing all the way to the critical point. So one caveat about our results is that we are focusing on the high temperature regime, right? So we prove optimal mixing of the Swendsen-Wang dynamics when beta is in the high temperature regime, strong spatial mixing holds, and beta is less than beta critical. Okay? Whereas we could make the case that perhaps the other regime, the low temperature regime, when beta is higher than beta critical, it's more relevant for the Swendsen-Wang dynamics. It's more relevant to prove result for the Swendsen-Wang dynamics there because that's where the global dynamics is slow. Okay, well, first, the fact that we prove this optimal mixing or the optimal order log n mixing for the Swendsen-Wang dynamics gives us a fast sampler that could be even faster than the global dynamics because the steps of the Swendsen-Wang dynamics can be parallelized quite efficiently, and you only need to take order log n of them, right? So it could be quite faster in practice, the Swendsen-Wang dynamics. And also our results shed some light on what's going on the low temperature regime. For example, we're able to show that when beta is larger than beta critical on C2, we can show that the mixing time is order n log n, and this improved by some polynomial factors the best known balance in that region. Okay, so here is a proof overview. Let's start with the proof overviews for the upper bound. Here we want to show that SSM implies order log n mixing of the Swendsen-Wang dynamics. So let me introduce this notation here, and this is the idea of we have a function for the from the set of configurations to the reals, and we look at the expectation of that function with respect to the measure mu. Right, that means that we sum over all the possible configurations. We look at the value of the function at that particular configuration, and we multiply it by the probability of the configuration. And likewise, we can define variance with respect to the measure mu. Okay. In our previous work, this work here in STOC a few years ago, what we show is that the Swendsen-Wang dynamics contracts the variance of any function f. Right. So if we consider the variance of a function f versus the variance of the function after one step of the Swendsen-Wang was applied. So this is captured by PSW. This is the transition metric of the Swendsen-Wang dynamics times F. If we can show this type of contraction here, then this implies that the mixing time of the Swendsen-Wang dynamics is almost, well, if delta is some constant, which is what we managed to show, delta is some constant. This is just order of log of 1 over pi mean, where pi mean is the minimum probability of any configuration. And that's essentially exponential in the number of vertices, inverse exponential in the number of vertices. When you take log of that, this gives you O of n. Okay, so this type of inequality here is equivalent to the Poincare inequality and gives you this mixing time bound. What we do in this work, if we do something analogous, is that we show that the Swendsen-Wang contracts the entropy instead of the variance. Okay, and this is this discrete contraction of entropy actually implies that the mixing time of the Swendsen-Wang dynamics is, again, you get this factor that is inverse of the contraction. In our case, it's some constant, so we get some constant here. But then instead of having log of 1 over pi mean, we get log of 1 over pi mean. In this case, the log n bound. Right. Now, this discrete contraction of entropy is a discrete time version. It is in fact a little stronger than the modified logs of inequality, in the sense that it implies the standard modified log Sobolev inequality. But at the same time, it's weaker than the also standard log Sobolev inequality. And this is important because log Sobolev inequalities, the type of log Sobolev inequalities that we can prove that are actually true for the Swendsen-Wang dynamics are insufficient to give you this type result for the mixing time. Okay. Okay, so now I'll tell you a little bit in just one slide how we go about proving this contraction of the relative this discrete contraction of the entropy. Okay, so for this we consider this the so-called Edwards-Sokal measure, which is a measure in a joint space. So this is a space where configurations have spin assignments, but also edges. Right? So the configurations are pairs of edges and spin assignments, and each configuration receives this probability given by this expression here. There's p, a p factor for each edge in the configuration, a 1 minus p for each edge that is not in the configuration. And then we only it's only supported on the set of edges that agrees with the configuration sigma. So what this means is that the endpoints of every edge in A has to have the same coloring sigma. Otherwise, the configuration has 0 probability. Okay? And P here is related to beta like this. P is essentially 1 minus e to the minus beta. Okay? So this is the joint Edwards-Sokal measure, and it's quite useful because the Swendsen-Wang dynamics is actually lifting the configuration from a spin-only configuration to a spin-edge configuration, and then projecting back down. So the Swendsen-Wang dynamics actually moving into the intermediate step of the Swendsen-Wang dynamics is in this joint space. And if you marginalize here the edges, the marginal of this measure is actually the Potts distribution. Okay, so we consider this joint measure, and we consider a particular type of entropy decomposition or entropy factorization in this joint space. This is what we call the spin edge factorization of entropy. And here, for every function, we want to show that the entropy of the function g is bounded by essentially here the entropy we factorize it in the entropy on the spins plus the entropy on the edges. Right? So let's parse this expression here. For example, this says that if we fix a spin configuration, we look at the entropy of G with respect to the entropy of the edge configuration, right? Because now the spins are fixed, all the freedom that we have is to pick the edge configuration. We look at that entropy, But in fact, we look at that the average entropy, right? We look at the average entropy over all possible spin configurations, right? So that's what these terms mean here. And this is an analogous term, but fixing the edges instead of the spin, okay? So this is what we call a spin edge factorization of entropy. Here is another form of factorizing entropy. In this case, this is not in the joint space. This is a factorization of entropy with respect to the spin space, to the configurations, the POTS configuration space. And here we factorize entropy with respect to the entropy on the even sublattice or in the odd sublattice, right? So we can always split the lattice in the points with even coordinates and with odd coordinates, and then we can tensorize the we say that that the even odd the entropy tensorizes or factorizes in the even odd is this type of inequality. Okay. So what we prove in this work is that this even odd factorization of entropy implies the spin edge factorization of entropy, and this spin edge factorization of entropy imply the discrete contraction of entropy, which we know implies the right bound for the mixing time. This is what we prove in this work. When we combine this with some previous recent work of two of our co-authors, Caputo and Parisi, in that work they show that the SSM property implies the even odd factorization. So following this sequence of implications, we obtain our result. Okay? Now, 2 points here is that these two implications, we actually prove them in more generality. Right? So the first one, this is the main technical result. Actually, our proof holds for all bipartite graphs of bounded degree. Okay? And in fact, this already, the point is that it can find applications in, we hoped when we proved this that it find applications in other setting, and I think there have been already a couple of results, follow-up work that actually use this more general implication. Okay? And the second thing that we prove here that the spin edge factorization implies entropy contraction. This actually holds for all graphs. Here we don't put any restriction on the graph. Okay? And again, this is useful for proving result about the Swendsen-Wang in other settings. Okay? Okay, so that's it for our proof of abuse for the upper bound. So now we'll just give you a one slide proof of abuse for the lower bound, which we also think has some interesting ideas. So here we show that SSM implies omega of log n, right, for the mixing time, and this matches our upper bound. Okay? So the high level idea here is that we adapt this powerful framework of Hayes and Sinclair for 2007 from proving tight lower bounds for the global dynamics, right? So this is the key here is that this work was intended initially for the global dynamics to prove lower bounds of the form n log n that matches the upper bound. The non-locality and synchronicity of the move of the Swendsen-Wang actually requires that we make several technical modifications to this framework, right? And there are a few observations that we have to make along the way. Perhaps the most important, perhaps the most novel technical ingredient in our proof is that we need to bound the speed of propagation of disagreements on the Swendsen-Wang move. So just to give you a rough idea here, suppose that we have we're considering this vertex here at the center of a box, and outside of this vertex, the configuration outside of this box, the configuration is all blue, and outside of this one is all red, right? So we would like to understand on the some couplings for the Swendsen, if there are some couplings for the Swendsen-Wang dynamics, for the step of the Swendsen-Wang dynamics, that can actually delay as much as possible the speed, the time at which these disagreements penetrate the center of the box. Okay, so this is in the Hayes-Sinclair framework. This is needed for the global dynamics. In the global dynamics, a little simpler because in order for the disagreements to propagate here, if we're always updating the same vertex in both copies, we need to hit something that is close to the disagreement and propagate step by step from the disagreements to the center, right? And that means that there have to be a path of disagreement, and you can count the number of paths and bound the probability of each path under the global dynamics. But for the Swendsen-Wang, the Swendsen-Wang is quite global, right? The Swendsen-Wang in one move potentially can actually provide the disagreements all the way from the boundary to the center. So we find a coupling that actually managed to avoid this. And for that, we need to use the SSM property, right? The SSM is actually not needed in the Hayes-Sinclair framework. And we also need to pick the starting configuration quite carefully so that we can control the spread of this element on the Swendsen-Wang dynamics. Okay? That's it. Thank you.